Again. Hello and welcome back to Calculus 1. We are starting chapter 4, so section 4.1 on minima and maxima. When we observe functions, right, the graphs of functions, we can observe the maximum and minimum points. So say that, why is this blue? There we go. So let's say that this is some f of x. It will continue going indefinitely down on both ends. We can observe the point here, which will be known as relative maximum, and over here a point that will be known as absolute maximum, and over here relative minimum. So graphs will give us a graphical representation of some applied situation. For instance, what's happening with the money on the stock exchange, or you can take a look at the distribution of power for the engine, or where. So there are countless examples of what a function could represent as we work on applied problems. Now, you want to see where is the maximum power, or maximum pressure, or maximum volume, or maximum amount of money you made, and also where's the minimum. You want to look for the minimum cost, right, or the minimum pressure, or something that is needed, minimum energy, right? Each state, each object tends to stay in its minimum energy state. So you want to know where these points are. So now I have the two words there. One is relative and the other one is absolute. And they mean exactly what they mean. So when I say a relative maximum, that means that it's a maximum in its own neighborhood, right? Relative to the neighborhood. Now, the other one is absolute maximum because that's absolutely the highest point on the entire graph. Now, this is the only minimum we have on this graph, but it's relative because, as you can see, if I draw the line over here, all of these points and all of these points are lower on the y value than that minimum. Therefore, it cannot be absolute minimum because there are lower points than that, right? So we can generate the graph that will have absolute minimum. It's easy, just x squared, right? So if you have x squared graph, well, this vertex here is absolute minimum. So it's not that they don't exist, it's just that, you know, our graph currently did not have one. So that's the story of the two words that we are going to be focusing on. So absolute and relative. Now, a relative also has local, depending on which book you would read, right? So you can say relative min or local min. And then you also have the absolute or global. So those are also words that will be used. So if I ever say local minimum or global minimum, you know what they mean. It's, again, relative or absolute. Now, we have definition for absolute minimum and absolute maximum, and that is clearly that the y value is either the lowest of all points or the highest of all points, depending whether you're looking for min or a max. So definition, this is just a paraphrasing the definition. The full thing is given in the textbook. It says that I'll just say over here that the absolute max is the highest point on the graph, and absolute min is the lowest point on the graph. So we have absolute min and absolute max, and then we also have the relative ones, but as I said, they are, you know, locally. So if you want to think about this absolute max, right, that would be like the absolute power, absolute king or president or whatever, and then you have all these other relative max values, which would be like governors or mayors or whatever, right? So, you know, the boss in their own backyard. Now, we want to also now think on when do these occur. If I draw, let me draw the same graph again. Observe that all of the tangent lines are horizontal. I need to write that in blood over here. All tangent lines are horizontal. Let me just, for min slash max, let's put that. So for min slash max, all tangent lines are horizontal. What that means is that horizontal lines have slope equal to 0. So when do these min and max value occur? They occur when the derivative is equal to 0. So I'll just put m equals 0, m equals 0, m equals 0. We also call this horizontal tangency. So if you ever see that wording in a problem, find horizontal tangency. Well, horizontal tangent line, the slope is 0. So I hope you see that this is the case. And just because of this, we have the definition for critical points now, right? Because critical point is the point at which the derivative is 0 or the derivative does not exist. So now, min and max are extreme values which occur at critical points. Definition of a critical point: an interior point C of the domain of f of x at which f prime of c is 0 or f prime of c does not exist, is called critical point of f. Now, I want to just reiterate this. To find critical points, set f prime of x equal to 0 and solve the equation. Also, observe the emphasis on also. All points where f prime of c does not exist are critical points. I'll put over here i.e. vertical asymptote. You are not going to find min and max point along the vertical asymptote, clearly, but it's also the part of critical points list. So you have to be careful about that. Now, I'll remind you that the function y equal absolute value of x is not differentiable at 0. Right? So the derivative doesn't exist there. It's a critical point by the also part, and we know it's a minimum, right? It's a v. So you have to be careful about these things. So 1 over x has a critical point at 0 because derivative doesn't exist there, but it's not a min or a max because it's a vertical asymptote. So, you know, it's a lot of things that come together on a pile here. So we have set the first derivative equal to 0. Why? Because first derivative is the slope of the tangent line, and any time the tangent line is there, the slope is 0. So it should be common sense that you are looking for these points by setting derivative equal to 0. That gives you an equation to solve. Now you also have to be careful that to spot any of those points which would give you the undefined derivative, because those could also be your min and max values. Good. So now we have a procedure to find these points. All right. So let's take a look at some examples. So we are going to look at clearly, so find critical points. Find and classify. Just find critical points. So function is just x squared. So we have f of x equals x squared. Then f prime of x is 2x. We set that equal to 0, and then we solve the problem. We get x equals to 0. Now, plug into f of x equals x squared to get y. See, this is one of the things that if you just stop for a second in your busy life and focus, it will be clear that you have to plug this back in the original equation. In pre-calculus, you learn that y is equal to f of x. Right? So, if I'm looking to a point, right, looking for a point, the point is going to have coordinates x, comma, y. Right? So it should be common sense that you will be plugging x in the original equation that is going to give you y back. If you plug it back into derivative, that's going to give you y prime, and I don't know of the point that it's defined as x comma y prime. Right? Make sense? So, points are defined as x comma y. The only equation that can give you y is your original equation, because this is y equals x squared. Right? So, you'll take your 0, plug it in the x squared, you will get another 0. So now, y is equal to 0 squared equals 0, and I have my critical point at 0, 0. So, this point, 0, 0, is either a min or a max. We know it's a minimum because it's x squared and it's easy, and we know, right, what it is. Now, obviously, for some spicier examples, you will have to do further analysis to figure out what it is. So we have our critical point, and in this case it's a minimum because we know, because it's x squared. Another example, f of x equals absolute value of x. Well, f prime of x does not exist at x equals 0, therefore there's your critical point. So plug this in plug x equals 0 into y equal f of x equal absolute x, and get that y is 0. So now we have our critical point to be again 0, 0, and it's again minimum because we know. Right, we know it's a minimum. It's a spike over there. Now, these are two problems where we really don't have to do any work, right? You should know by now if the problem says x squared or absolute x that it has a minimum at 0, 0, because you know those are basic functions that we all have memorized. This method is used for something like this. Let's say x squared ln x. Now, can you look at this and tell me where the point is? And the answer is no, right? We have to do some calculations. So now, first off, I need to know certain things. In order for this to work, I need to know the domain, because I can't be looking for a point that it's not in the domain, right? That would be silly. That would be like you going to ShopRite looking for this classroom, right? His classroom is not in ShopRite, right? ShopRite has the food, and they have the warehouse and the bathroom and the money room, right? They, like with a safe, that's what they have. They don't have this classroom there. So the trick is, the first order of business is to figure out what the domain is, so that as you are calculating these things, all of the points that do not fall into that domain, you can just ignore them. Because there will be points that you will be obtaining in this example also that can't be used. So now the domain for this is 0 to infinity, not including 0 and not including infinity, obviously. The reason is there is a vertical asymptote at 0, and ln works only for positive numbers. If you plug in negative number in ln, you will get imaginary numbers, complex numbers. So we have a requirement of the domain to be 0 to infinity excluding 0. So it's open set, open interval. Now we just do the regular stuff. We know the procedure. Just take the derivative and set it equal to 0. See what happens. So f prime of x is, well, this is a product rule, so let's have fun. Copy the first times derivative of the second plus copy the second, which is ln x, times derivative of the first, which is 2x. So now f prime of x is equal to, we have x plus 2x ln x. Remember what I said 15,000 times. Factor, 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 get used to it, right? Because when you set equal to 0, there will be work to be done, right? So f prime of x is equal to factor, there we go, x, and then 1 plus 2 ln x is the leftover. And this is what you set equal to 0. I'll put that in red because that's new stuff. So everything you see so far is old knowledge. How to do the product rule, what's the derivative of ln, right? Figure out domain, that's pre-calculus. So we are starting our new, right here, when I say equal to 0, right? That's that. So now you have two equations, x equals 0, and 1 minus 2 ln x equal to 0. Now, I hope that you see that we gotta throw this one away, and I'll just write domain. It's not in the domain. Domain says anything after 0, but not 0. If I get x equals 0, not in the domain, throw in the garbage. The next one is over here to solve. So I have that 1 is equal to 2 ln x. Ln x is equal to 1/2. We are going to e both sides and get x equals square root of e. Right? E to the half is the square root of e. So now I have to take this and plug back in the original problem. So plug into f of x to get y. So f of square root of e is square root of e squared ln square root of e. We have to compute this. Square and square root cancel, just gives us e. Ln to e to a half, half goes in front, and then you have ln e. And the ln e is 1. So the whole thing is just e over 2. So critical point is at square root of e, comma, e over 2. Now, what is it? Is it a min or is it a max? Which one of these two? All right, so now it's going to be a little bit tough, but as we move along to next chapter, next section, actually, 4.2, we will learn more powerful and easier techniques, less tedious techniques, to figure out whether it's a min or a max. The only thing that you have available to you now are two things. One, you already know what the graph looks like x squared or absolute x, so you know whether it's min or a max. The other one is to do the tedious, plug the points and check. So let me give you a quick rundown. When something is a max, its y value is max. So, and that happens for the x that produced that max, which is our x for the critical point. Observe that if you move either left or right from that x, any other y value is going to be lower. So you see that I have a square root of e. I'm going to compute that as a decimal. I'm going to get some decimal there. And then I'm just going to move a little bit to the left and a little bit to the right and see if I'm getting a smaller or larger value than e over 2. Let me actually do, so I'll do two graphs. This or this. This one, this point here, is root e over 2. This point here is root e over 2. So it's one or the other, because this is either a min or a max. There is a third option, inflection point, but we'll discuss that later. So now, square root of e is approximated by, and now you take your abacus and you figure it out. So square root of e is about 1.6487, and e divided by 2 is about 1.3591. So these are my two values. Since I don't have any other means of testing this, I'm just going to say what is the f of 1.7? Right, as the input. Because I know if I use root e exactly, I'll get e over 2. And now that e over 2 is either, right, so now since I'm using, let me put this on x-axis. So this point here is 1.6487. Now, I want to compute at 1.7. Now, 1.7 is a little bit to the right. If this point was a max, the y value of 1.7 will be lower than this number. If the point was a minimum, it will be higher than this. That should be some common sense when you look at the graph. So, what do I have? I have 1.7. So now what I do is I just compute this 1.7 in original. So it's a 1.7 times ln of 1.7 squared times ln of 1.7. So we just compute that. Again, this is an annoying way to do these things because we don't have anything better yet. So the answer that I'm getting is 1.5335. That's larger. This one is larger there. So it's this situation. So it's a minimum. So let me go through the logic one more time over here on the board. I'm just going to create a stick. All right. So we did calculations, and we know that our critical point, which could be either min or a max, is at this value, root e over 2. Now, these are the decimals for root e over 2. Now, I would like to know if this point is a min or a max. If it's a max, that graph would look like this, and then if you move a little bit left from x value or a little bit right of the x value, the y value should be smaller than this number. Because this one is a max, that means that every other point is lower. If the point that we have is a minimum, then all other points, when you move to the left or the right, will be higher. Because this one is the minimum, the rest have to be higher. In order for you to be the minimum, everyone else has to be high, right? For you to be the shortest person in class, everyone else has to be taller than you. That's the logic that we're using. Or for you to be the highest, the tallest in the class, everyone else has to be shorter than you. So what am I doing now? I'm just going to see what the decimals are for these two numbers, right? Cut it at 4 decimals or whatever. And then I'm going to pick a value that it's to the side. It doesn't matter which side. It's to the side of e. So instead of 1.65, I'm using 1.7. It's close, and it's to the right. Computed that at the original problem to get 1.53, and this is 1.35. So my value is taller, right? That means that the original value is shorter, which means the minimum, right? Because this one worked out to be higher. So it's this situation here. The point I'm computing, this is 1.7, and this is 1.6, which is the original one. 1.7 turned out to have a higher value. So the original point is the minimum. This is an annoying way to do this because it is, calculations and all these things. Next class, we are going to learn much better way to deal with this, and you will have better tools. Now, I mentioned the third type of a creature, not a min, not a max, but something is called inflection point. Inflection point will actually be covered next time because that is something that arises from the second derivative. But you need to know about it now because as you attempt the homework or try some things, it might show and then you might say, well, this doesn't fit anything that we talked about. And it doesn't. Let's talk about f of x equals x cubed. Take the derivative of this thing, and you will hopefully get 3x squared. When you set it equal to 0, you get x equals 0. And then when you plug that 0 in original function, you get another 0. So you get that the critical point is at 0, 0. Is it a max? is it a min? And the answer is, it's not a max, and it's not a min. Right? Just think of the graph of x cubed. The graph of x cubed is this. And 0, 0 is here. So, like if you're looking from the left, it's a max. If you're looking from the right, it's a min. But it's actually neither of the two. So we are going to define these points as inflection points later on, well, tomorrow. And they will work with something called change in concavity and blah, blah, blah. But, you know, it's good to know right now that they just exist. So if you run into these points, you know. Now, how do you know that the point is inflection point? Well, you know how over here I told you that we are looking for min or a max? And because we haven't learned of inflection points yet, it was pretty much guaranteed that it's going to be one or the other. Your job now is to compute point to the left and point to the right. And if one turns out to be lower and one to be higher, it's inflection. If they're both higher, it's a minimum. If they're both lower, it's a maximum. So now the annoying method has minimum with 2 points higher, maximum with 2 points lower, and inflection with 1 lower and 1 higher. So now you will have to compute 2 points, one to the left of the critical and one to the right. Just, you know, go 1 decimal over. That's all you need, right? If your critical point is at 2, use 1.9 and 2.1. That's it. So just go 1/10 to the left and 1/10 to the right. Compute both. And again, right, if you are getting 2 larger numbers, your original critical point was a minimum. If you're getting 2 smaller numbers, your original point was a maximum. And if one is smaller, one is bigger, could go the other way, right? One is smaller, one is bigger, then it's inflection point. It's not a min, not a max. And that's the basic. Now we just have one more add-on to all of this, and that is that all the functions we discussed so far, they go to infinities, right? The domain. What happens when you have, so what happens when you have the restricted domain, when you have line segment, function that goes from point to point and it stops? Well, that one is guaranteed to have min or a max on its domain. You see, if I draw a line segment, like these functions here that I have, these guys are infinite, right? But what I can have is the function that it's not truncated, on a restricted domain, right? So you have a line segment. You have this, which ends, right, between A and B. Now we see that this is ABS min, and we see that this is ABS max. I can have something like that, right? Again, this is A, this is B, and here's your ABS max, and here is the ABS min. The theorem is that if you have these finite lines, right, that go from A to B, then your min and max are guaranteed. We're not considering, obviously, constant function, because constant function cannot have min or a max because it's constant, right? You have to have a change in slope, right? Positive and negative slopes in order to have change in y, because y is the one that measures. So a straight line is not considered, but everything else is. I mean, constant line, straight line. You can see the straight line over there, which is fine. So now you can come up with any type of a function. Any type of a function you want, right? It will always have absolute max or absolute min. You just have to find them. Now, you use the method we just did, derivative equal to 0, to take care of all the eternal ones. And you will just set, you will compute the values for the endpoints, and then the highest of all values is absolute max, the lowest of all y values is absolute min. Let's take a look at the example to put all of this into perspective. Wow. It went straight to homework without making me wait 55 minutes. This is great. So let's do something that it's quick and simple and nice, like problem 24. It says f of x is equal to 1/8 x cubed minus 1/2 x on -1 to 3. Great. Now, all I care about is that there is some kind of a function that goes from -1 to 3. So I can immediately find f of -1 and f of 3 and have those ready, and then just do the inside of the line. Okay, so f of -1, that's going to be -1/8 plus 1/2, which is times 4/3/8. So the y value is 3/8. So I have -1/3/8. Then I have the second one, that's a 27/8 minus 3/2. This is times 4/12, so 15/8. So I have 3 and 15/8. So all I did is I computed the endpoints to find their y values. Again, I don't know if the endpoint is the highest, because I can make endpoint not to be the highest. See, this is the endpoint and the highest is over here. So we don't know. We have to find all of them, and then we'll simply pick the largest y of all y's, and that's absolute max. So what I'm going to do now is do the derivative. I have to do all of the interior. That's 3/8 x squared minus 1/2. And we set this one equal to 0. We can multiply through by 8 to get 3x squared minus 4 equal to 0. I'll just say times 8 over here. And then we have that x squared is equal to 4/3. And x is equal to plus minus 2/√3. So those are my critical points. 2/√3, positive and negative. So now, calculate the function value at 2/√3. I should have rationalized that. So I have 1/8 times 2/√3 to the third power minus 1/2 2/√3. Alright, the 2's will cancel. 8 and a 2 will cancel because 2 cubed is 8. And all we are left with is 1/√3 cubed minus 1/√3. So that's further equal to 1/3√3 minus 1/√3, and then times 3 for common denominator. We have -2/3√3. So this point that we just computed is going to be 2/√3, comma, -2/3√3. It bothers me, this √3 in denominator, but yeah. It bothers me. Root 3 becomes negative 2 root 3 divided by 9. And over here, root 3 is 2 root 3 over 3. So the critical point is at 2 root 3 over 3, comma, negative 2 root 3 over 9. One more. For negative 2 root 3, what changes? Well, the sign change. Other than that, everything stays the same. So when you cube a negative, it remains, because cube, 1, 2, 3. 3 minus signs, right? So 3 minus signs together will give you a negative. So we have this one. That will be negative 1 over 8 times 2 over root 3 cubed. These cancel again. And now it's plus 1/2 2 over root 3. And then 2's cancel. So what we have now is negative 1 over root 3 cubed plus 1 over root 3. Standard stuff, negative 1 over 3 root 3 plus 1 over root 3 times 3 for common denominator. And this time around we get positive 2 divided by 3 root 3. Rationalize that. 2 root 3 over 9. Another critical point. At negative 2 root 3 over 3, comma, 2 root 3 over 9. We have four points to consider. So the first 2 points, negative 1 and 3/8. What was the second one? Did anyone write it down? So 3 and then 3 over 15? Like that? You said 15 over 8. Like this. Thank you. Then we have 2 root 3 over 3, comma, negative 2 root 3 over 9, if I remember. Yep. And finally, negative 2 root 3 over 3, comma, 2 root 3 over 9. All right, so immediately, without any thinking, this is our absolute min, because it's the only negative number, right? So it has a negative y value. That one is the lowest of all. And I just need to see which one of these is the highest of y values, and that's absolute max. Now, clearly, we're going to throw away the first point, because 3 over 8 is definitely smaller than 15 over 8. So that's out. And I just need to compare these guys, right? And you can compare the decimals, right? Figure out what 15 over 8 is in decimals, and figure out what the 2 root 3 over 9 is in decimals. And then whichever one is larger number on the y-axis, on the y coordinate, that's going to be absolute max. So 15 divided by 8 is 1.875. And the other one is 2 square root of 3 divided by 9 is 0.385. So this one over here is absolute max. It has the highest. Well, that's almost 2, right? 16 over 8 is almost 2. Over here, root 3 times 2, that's almost, it's less than a half. Well, it's 0.385. So the only thing that we are adding new to the process is this calculation of endpoints, where we get the other 2 points that are in the mix. We solve the derivative equal to 0 the same way we always would, and we come up with critical points, and those critical points need y values, which we obtained from the original equation. They need y values because we are supposed to compare and check y values, right? And that's that. Let's do one more example and call it a day. Now let's do something with ln or a trig. So I know how much you love that stuff. You go home, you have a little like area, you worship the ln and what happened?
To make a sacrifice to the ln.
Yes. Like one of your twins, right? So what should we do? There is well, 33 looks cute. It's 1 over x plus ln x. That looks cute. Then 34 is x squared minus 2 ln x of x squared plus 1. Then 35 is x squared plus square root of x plus 1. Whatever, huh? For a moment, it looked like you're going to cough, and you just don't do it. All right, fine. By popular demand, 33. You all hear people screaming, 133. Fine, here we go. So function is given as 1 over x plus ln x. And, oh, well, this one is not giving us the interval. No, I mean, we can find the domain. Domain is not an issue. But, so I mean, 33 already is fine. Well, so what would be the domain? We know that 1 over x looks like this. So it has all numbers except 0. And then ln x looks like that, has only positive numbers and no 0. So when you combine these two graphs, right, it's going to be 0 to infinity. You have a vertical asymptote at 0, and then only positive numbers, because ln is only handling positive numbers. Now that we have this, we take the derivative, which is negative 1 over x squared plus 1 over x. And then we set that equal to 0. So now we need to solve this thing. The way to solve this thing is to move this one to the other side and then cross multiply, right? So we are going to say that 1 over x is equal to 1 over x squared. And when you cross multiply, you get that x squared is equal to x. All right. To solve this equation, you have to subtract x on both sides. Yeah, I understand that you would like to divide both sides by x, but then you would lose the solution. All right? I will never forget my pre-calculus 2 exam where I divided both sides by tangent and lost the solution. It was 97. Punched like 3 holes in a concrete wall because of it, obviously with a sledgehammer, which shows conviction. I had to go rent the thing and then bring it home, figure out how it worked, right, and then. But anyway, so when you're solving these equations, do not cancel. Equations don't like that because you lose solutions. You subtract x, and you get x squared minus x equal to 0. And then x minus 1 equal to 0. X equals 0, which we have to throw away because of the domain. And then x equals to 1, which is what we keep. That is in the domain between 0 and infinity. Now we plug that back into our original equation to find y. So y is f of 1, which is 1 over 1 plus ln of 1. That is 1 plus 0, which is 1. So now we have 1, 1 critical point. The last question is it a minimum or a maximum? What is it? And the way you would figure that out is to, as I mentioned before, you compute at 0.9 and at 1, 1 and see exactly what happens on both sides. So I need to compute f at 0.9 and I need to compute f at 1.1. Those values will be either bigger than this y value or smaller, or one bigger, one smaller. So let's go. We have to compute, so we have 1 divided by 0.9 plus ln of 0.9. And the value I get is 1.0057. Now I have to do the same thing. 1 divided by 1.1 plus ln of 1.1. And this gives me 1.0044. So the point is a minimum, because the y value that I have is 1 on the elevation, right? Elevation 1. And the other two values, when I go a little bit to the left and a little bit to the right, they're above. So you see how you can fit something that looks like that. So this is 1, this is 0.9, and this is 1.1. And we see that both of those worked out to be above. Therefore, the point that we are observing is a minimum because the other 2 points are higher. So just use, some common sense for that, and you should be fine. I don't have the closing. That's that. Bye.